All right, so this is 10.2 number 2. We're talking about areas between curves. There's a second method I want to talk to you about. It's really not that much different than the first method. The first method, if you recall, this is a more complicated question we did last class, right? But a simple question, let's go back. Simple question like this. So what we did here, and I think this is the exact question we're going to do with new method here. What we did here is we found the area, we found the area under the upper boundary curve, and that's the whole area, under the curve and all the way down to the axis there, right? And then we subtracted the area under the lower curve. So that's sort of method 1. That's pretty standard, pretty typical. Method 2 exists to simplify things a bit for you, but you only can use this method 2 when one function is always on top of the other function over the interval with which you want to find the area between curves. So again, we're still finding area between curves, but one function has to be the upper function the whole time. Then you can use method 2. So in the case where one function is always greater than or above the other function, so if function A is like this, and function B is like this, okay, it's always underneath. You can go from anywhere, A here to B here, and you can find the area in between those if one function is always greater than the other. Then what you can do is you can, before you do any calculus, you can subtract the two functions and find the area under the one new function. So you would find the area under this new function, and of course above the x-axis, and it will be the same area as between the original functions. So an easy way to explain this, guys, would be just like this. Watch this. I'm going to redo this example above. I'm actually going to put the lower function as a horizontal line. Okay? Now, between A and B, right here, this is the area, right? Now, what happens if I were to subtract these two? This function minus the constant function. All we would be doing, and I want to see if I can just grab what I want here. I don't know if I can. Oh yeah. All we would be doing is moving the function straight down. Look at that. You see this blue function that was up here has now been subtracted by this constant. And look at what we have. The area under the new function, because here's the old one. Right? There's the old one. I just subtracted the two. So that's the same area. So if it works for horizontal lines, it will work for curves that are not horizontal. So let me just show you here. Okay, so this one, I don't know why this is so big here. Interesting. Okay. I'm going to just make this a little smaller. Hang on. Okay, I'm going to bring this up here too. All right, so go back to 100% here. All right, so the example says, it's still not very good. The example says, find the area between x squared plus 1 and y equals x from 1 to 3. X equals 1 to 3. So we've done this question before. I just showed you this question. Now, if we subtract the upper function minus the lower function, okay, we would have a new y, and let's call it h of x, okay, or h of x, is x squared plus 1 minus x. X squared plus 1 minus x, which gives us this function right here, x squared minus x plus 1. Okay? Now you're saying, how does that relate? Well, over here, I actually have a sketch of this graph. This is x squared minus x plus 1. So what happens here is, first of all, we just have one function to deal with, not two. So that's handy. Oftentimes, subtracting the functions is deathly easy. It's really quick. And so finding the area under one function is just a little bit less work. So a lot of times this is going to be great. Now 1 to 3. So here's 1, and here's I think that's 1. This is 3. I don't have the markers down there. But if we were to extend this. So this area right here, that area under the curve is the exact same as this area between these two curves. So that r there is the same as this r. And finding that is just a little bit simpler because we only have one function to deal with. So if you recall from yesterday now, or the last class, when we had to do, let me get back to it. You see, this is the same question. And I had to find the area separately underneath the upper curve, and then the area underneath the lower curve, right? And then subtract the two to get the area that's left over, this r. Well, now, with this method, I do a quick subtraction of the original functions, and then boom, I just find the area under this curve now. So now I focus on this one. So we're going to have f of 3 minus f of 1. And the antiderivative function of the new one is going to be, what's the antiderivative of x squared? 1 over 3x cubed, very good. What's the antiderivative of x? 1/2 x squared, great. And what's the antiderivative of 1? 1x, or just x. Well, again, when we're finding area, when we're finding a number answer for area, we don't need to be putting plus c in this, not in this case. So that, when we get to chapter 11, we'll talk about definite integrals and indefinite integrals. So this would be the case where you don't have to worry about plus c because we're not stopping here. We're actually finding a number for that area of the shaded region, okay? Yeah?
Would it be correct to just capitalize the h when it's an antiderivative, or do you have to?
Yeah, so you can, sure. If this is the function, you could write this as capital H too. If I've named this as h, you could write this, I think if that's what you're asking. Yeah, you could say that this is capital H and capital H, yeah. Generally, generally the capital F is the antiderivative of function f. So this is fine, I guess. Yeah, that's good. All right, so let's do it then. So I've got 1/3 of 3 cubed minus 1/2 of 3 squared plus 3 minus 1/3 of 1 cubed minus 1/2 of 1 squared plus 1. Which that's 27 over 3 is 9. I feel like we've been here before, just in the last class. 9 over 2 plus 3 minus 1/3 minus 1/2 plus 1. So that's going to be 9 and 4.5 and that's 13.5 plus 3 is 16.5 minus, what's this, 1/3, okay. Probably should work in fractions here, I guess, but 1/3 minus 1/2, so it's going to be 2/6 and 3/6. So it's negative 1 over 6 plus 6 over 6 is 5 over 6, I guess. 16.5 is, what's that, 33 over 2. All right, anyways, times 3, so 99 over 6 minus, oh, something disappeared here. 5 over 6, which is what? 94 over 6, which is what? Divided by 3? I'm divided by 2. What was the answer before? Let me get this right. Am I doing any of this in my head correctly?
Before was 20 over 3. I get to 47, but 47 over 2. Yeah, I got 20 over 3.
All right, so this is 15 over 2.
Yeah.
Good. So that's not times 3 was at 45, which is 40 over 6 or 20 over 3. Good. Okay, we got that figured out. And that's units squared. So it does match up with what we did before. So again, real quick, let's get back there to this question right here. And I don't know, you can compare. Maybe I'll just kind of clip this, copy this so we can compare them side by side if you want. I mean, it should be a little bit easier to do a quick subtraction first. And so side by side, okay, that didn't copy correctly, but anyways. Would you say that method 2 is a little bit more straightforward?
Yes.
As long as you can do your fractions correctly? Okay. All right, let's do some other examples then. And let's see how this can simplify things. All right, some more challenging ones. Oh, well, we can do one like this too. So let's actually just check the textbook real quick. All right, so here's 1G from your assignment. Let's do this one together from scratch using method 2. Find the area between the two curves using method 2. So we have y equals 2x minus x squared. We could sketch this out a little bit, to check it out. We would need to check to make sure that one graph is over top of the other graph the whole time. And there are there's a parabola and a line, so probably going to be one graph is on top of the other one the whole time. Let's just do a quick sketch. So y equals negative x is going to look like this. It's going to be a negative slope here, like going through 0, 0 with a slope of negative 1. And then 2x minus x squared. So that's negative x squared plus 2x plus 0. So we are going to have a 0 as an intercept. I'll do this one maybe in red. And if you want to do a quick table of values, I mean, what's 1? Well, y equals 1 is going to be 1 squared plus 2 is 3. So you're going to have like a 1, 3 up here. Okay. And if you want to do something like, let's do 2, see what happens. 2 squared, that's going to be negative 4 plus 4 equals 0. So at 2, we've got, looks like 0 again, is that right? So you want to sketch this, and it looks like we have a parabola that opens downward, has a intercept of 0, and x-intercepts of 0 and 2. What we could do is factor this as well. Take a negative out. You have negative 1, you have x here, you have x minus 2. So that's factored, right? So that's 0 and that's positive 2 for factors. So we could do it that way too. So we are going to have to find out what value this is right here, I guess, when those two meet, because we want to find out the area between the two curves. So let's see if our method 2 works here. We definitely have the parabola as the upper function, but I need to know now what what a is and what b is. So let's put these two together. Equals negative x. And so that's going to be 0 equals x squared. If I let those equal each other, x squared minus, 2x minus x, so that's going to be x squared minus 3x. So those are the solutions are going to be x minus x and x minus 3. So it's going to be at x equals 0 for this factor and x equals positive 3 for this factor. So that means that we're going to go all the way 1, 2, all the way to 3. So this is not to scale, I guess, but 1, 2, and then it'll be 3 down here somewhere. Okay, so it'll be 3. So we're going to go from 0 to 3. X equals 0 to x equals 3. All right, so we know the parabola is always on top. So let's do method 2. Let's do a quick subtraction first. So 2x minus x squared, and then we'll subtract a negative x. So that's going to give us a new function. If we do h of x here, that's going to give us a new function of negative x squared plus x plus 2x, or negative x squared plus 3x. Something like that. Look good? Let's see what the antiderivative function of h of x is then, because this is going to be a new function, and we're just going to find the area underneath that new function. So let's see what, and we don't have to graph it. We could, but we don't have to. So the antiderivative of negative x squared is?
Negative 1/3 x.
Yes, negative 1/3 x cubed plus 3 over 2 x squared. Perfect. And if we were finding an indefinite integral or the general antiderivative, we put plus c. But for this one, we don't have to, because we do have end values, a and b. We're going to find the area underneath those. So we're going to do h of we know our intersection point is 3 minus capital H of 0. So let's go ahead and do that. That's going to be the area underneath this new curve. So negative 1/3 of 3 cubed plus 3 over 2 of 3 squared. Hello. Minus, thanks. Negative 1/3 0 cubed. Yeah, we're glad you're alive. Plus 3 over 2 0 squared. Which, those are just zeros, so that's no big deal there. So that's going to be negative 27 over 3 is negative 9. This is going to be plus 9 times 3, 27 over 2. Right? Squared times 3 times 7 over 2 minus 0. So that's 18 over 2. 27, that's going to be 9. Positive 9 over 2, I guess. Equals 4.5, or just 9 over 2 is a good answer. Units squared. Okay. So that's what we get for this question, and that is G. So that's the question they get in the back of the book for sure. So that's good. So it doesn't matter if that area, if part of this area between the curves is underneath, above, underneath, doesn't matter. This rings true the whole time. So it doesn't matter where this x-axis is, right? If this x-axis were down here, the area between the curves would still be the exact same, right? If the x-axis was up here, the area between the curves would be the exact same. As long as you use the upper function as the top one and start with that one. All right? So in a question like this, the sine and cos one that we did, this one's a bit tricky because you can't do this because the functions take turns being the top ones, right? If it was just from 0 to pi over 4, then you could do this sort of method too and subtract the 2 and go from there. But you still kind of have to piecewise things. So this section 1, you could do this method too and say, hey, this is cos x minus sine x. And that's the combined subtracted function. Go ahead. This one is sine x minus cos x. That's the combined function. So instead of doing 4 pieces of this question, you only have to do 2 pieces, if that makes sense. So there's a little less work with this method too. All right. Okay. Any other questions from your homework? I can show you. Here's 2A. This is kind of a mess, but anybody else have any problems with question number 1? I don't know. That's 1K from somewhere. Do you guys have to do K, right? 1K?
Yes.
Yeah. I can maybe talk to you about 1K if you want. Okay, one more question here. This one's a bit tricky. Y squared equals 4x. Now, you haven't seen anything like this before, right? Y squared equals 4x. You've seen parabolas, y equals x squared. Well, x equals y squared is flipped around sideways. It's not a function. It's flipped around sideways. Well, what you have to do here is you have to get y by itself. You have to actually isolate for y for these things. So y is root 4x. Now it could be plus or minus root 4x. So positive root 4x would look like this, right? Minus root 4x would look like this. That's where you get your sideways parabola from. You see, plus or minus. Now we might not have to use both of these, so we'll just see. But y here equals, what's that? X squared over 4. Or 1/4 x squared. So 1/4 x squared, this is going to be, like this one over here is obviously at, well maybe not obvious, but it's going to be sort of centered at the origin there. That's the red one. And then the blue one here is going to be a parabola that has an a value of 1/4, so it's really flattened out. So that's going to, be pretty flat, but it's also going to have a vertex at 0, 0. So we don't need this negative half. We're just going to deal with the positive version. questions about that so far? Okay. So we got a parabola and we have a square root function. Okay. Okay, so where is this? We need to find intersection point. So we need to let them equal each other and see what we can do to solve. So root 4x equals x squared over 4. 4 root 4x equals x squared. All right. Should we take the square root of both sides here maybe? Let's take the square root of both sides, see what we get. We get 2 times 4x equals x. Square root of this, square root of this. No, we're not squaring that, sorry. Taking the square root of both sides here. This 4 can come out. So that's going to be 8 root x. Let's do this way first. 8 root x equals x squared. I guess we could just kind of do this now. X squared plus 8 root x.
We're trying to solve for x though.
Yeah, we're trying to solve for x. Taking the square root of this one is not, I don't know if that's a great idea. So you're trying to find out where this is, where this intersection point is, right? So where does this equal 0? You could use graphing technology to find the x-intercepts of this, or algebraically only. Probably best thing to do would be to square both sides here to get rid of the square root. And we get 64x equals x to the 4th. Divided by x, 64 equals x cubed then, which x equals 4. Yeah, we don't see the x equals 0 in this way, but I guess you could factor this. When we divide by an x, we kind of get rid of the x equals 0 factor. So again, backing up, maybe the best way to go here is actually to, once you get to this point, make it a 0, and then go x to the 4th minus 64x, and then you won't miss the 0. So then this is 0 equals x times x cubed minus 64. Then you see that here's the 0. So x equals 0. And x cubed minus 64, if you let x cubed minus 64 equals 0, then that's where you get your 4. Okay? So, yeah, be careful with that one. Probably get rid of the root. Get rid of the root. If you have graphing technology on your test or your assignment and you want to find the roots that way, go ahead. Algebraically, don't miss the 0. Don't divide by x if you divide by x when you're solving, you might miss a factor. Yeah. But I knew it was 0, so that was not a big deal. But here's both your factors. Okay. So 0 to 4, that's where we're going to settle in there. Everybody good so far? Thoroughly confused you with that last one? Yeah. Sorry. Kind of. Okay. All right. So can we use method 2 here? Which one's on top? This one's on top all the time. So can we use method 2?
Yes.
We can. So h of x, or whatever, your new y of x, I don't really care. Root 4x minus, I'm going to write that as 1/4 x squared. And this x is underneath the root sign. So this actually could be written as 2 root x, I suppose. If we're finding the antiderivative, can we use the power rule on a square root?
Yes.
That's actually x to the 1/2, right? So are we okay to like add 1 to this? Does it work for fractions too? Yeah, it does. Okay, so let's find the antiderivative function. So if I add 1 to 1/2, what do I get?
3.
I get 3 over 2. If I divide by 3 over 2, that's the same as multiplying by 2 over 3. Does that make sense? If we go to 3 over 2, the dividing by that is like flipping and multiplying. Okay, so then this is, that's going to go up to 3, so that's going to be x cubed. I got to divide by 3. Well, I already have a 4 in the denominator, so that's 1 over 4 times 3. Or 1/4 divided by 3 is 1/12. And this, I will simplify that to 4 over 3. Okay. Good to go so far? Okay, so let's do h of 4 minus capital H of 1, which turns into this. 4 over 3 times 4 to the 3 over 2 minus 1/12 4 cubed minus 4 over 3, 1 to the power of 3 over 2, 1 over 12, 1 cubed. Actually you're right, it should be 0. That should be 0, thank you. It's 0. 0. What one I'm looking at. So these are just zeros here, so those are gone, and this is going to be the square root of 4, that's what that 2 means. So that's just 2, cubed is 8. 8 times 4 is 32, 32 over 3. Minus, this is going to be cubed at 64 over 12. 64 over 12, 16 over 3. Which is going to end up to be 16 over 3. Units squared. All right. Okay. Double check everything there. I think everything looks good now. All right. Can you guys do that on your own now?
Yes.
Think so? Awesome. All right, so just a reminder, MrMathWell.com, all the videos, including this one I'm making today, will be up there. And your homework is up here for chapter 10. And I would like you guys to try that letter N. So here's the homework for chapter 10.2, but I would like you to add one N on there too, if you can before the exam, because that's a little more challenging one, which I don't know if you've got, are you doing I? Let's see, Akajikmo. Okay, I is not too bad. I is not too bad. N is that other one that's a little bit tricky. So I won't add it right now, but maybe as a review you can do one N.